Hello everyone, welcome back to ChemOrgChem. So in our channel, we have been exploring the name reaction involving organometallics. So in continuation of our name reaction series, today we are going to explore TSUJI-TROST reaction or TSUJI-TROST allylation reaction. So if you are new here, don't forget to subscribe and hit the bell icon for notification. So let's see TSUJI-TROST allylation reaction. First, what is TSUJI-TROST reaction or allylation reaction? So this is palladium catalyzed reaction of nucleophiles with allylic compounds by pi-allyl palladium is known as TSUJI-TROST reaction or TSUJI-TROST allylation reaction. So this is the general scheme for TSUJI-TROST allylation reaction. So allylic substrate in the presence of palladium catalysis which generate their corresponding pi-allyl palladium species which then undergo nucleophilic addition with various nucleophiles that generate their corresponding allylic substitution product. So this reaction requires palladium 0 catalysis. However, when we use palladium 2 catalysis, we need suitable ligand in order to generate palladium 0 species in situ. And another important factor is we need base stoichiometric amount for this reaction. However, neutral condition also useful for this allylic substitution reaction. So in place of R1 can be hydrogen, alkyl or aryl. In case of X, there are lot of leaving group can be useful for this TSUJI-TROST reaction. In case of palladium complex, so palladium tetrakase and tris dibenzylidine acetone, palladium, these two complexes are commonly used for this TSUJI-TROST reaction. In case of palladium 2 complex, we need suitable ligands such as triphenyl phosphine or dibenzylidine acetone. So let's move into the catalytic cycle. So as per our previous palladium catalyzed reaction, this reaction also initiated by palladium 0 catalysis. So when we take palladium 2 pre-catalyzed, so we need suitable ligand to generate their corresponding palladium 0 species, which is a 14 electron species. So after the generation of these 14 electron spaces, which readily undergo coordination or complexation with allylic substrate, so which generate their corresponding palladium complex, so which is 14 electron species, so which then readily undergo oxidative addition to generate their corresponding eta 3 palladium complex, so which is 16 electron species. So after that, which quickly undergo ligand exchange with this pi complex. So here you can see that, so ligand replaces with our X group, so which generate their corresponding eta 3 cationic complex. So after that, this quickly undergo nucleophilic addition with nucleophile. So in this step, nucleophile attack this terminal carbon in order to generate this corresponding palladium complex, which then quickly undergo decomplexation reaction to produce allylic substitution product. So this is the general catalytic cycle for TSUJI-TROST reaction. However, depends on the nucleophile. This particular nucleophilic addition step is slightly different. So let's see how this nucleophilic addition step is different. So next we are going to see the soft versus hard nucleophiles in particular nucleophilic addition step. So when we use soft nucleophiles, so this readily attack the terminal carbon of this pi allyl complex, so which then produce this corresponding palladium complex intermediate, then followed by decomplexation which produce their allylic substitution product. So here you can see that when we use hard nucleophile, so this particular nucleophilic addition step is slightly different. So now nucleophile directly attack the palladium center, so which then produce this corresponding palladium complex, so which undergo reductive elimination to produce their corresponding allylic substitution product. So especially here you can see that why nucleophile particularly attack the terminal carbon, why not this carbon or this carbon. So let's explore the regioselectivity involved in TSUJI-TROST reaction. So now you can see that So here R1 is bulky when compared to the R2 group. So when react with this allylic substrate in the presence of palladium zero catalysis, so which produce their corresponding pi allyl complex by oxidative addition with inversion. So here you can see that the top phase is highly shielded, therefore our palladium zero interact with this alkene by bottom phase, so which leads to generate their corresponding pi allyl palladium complex by bottom phase. So now you can see that so our nucleophile can attack this carbon or this carbon. So how the regioselectivity is detected in this reaction? The regioselectivity of the process depends on the several factors. For example, the charge distribution in the intermediate of pi allyl palladium species, which favors the attack at the more substituted allyl terminus. In case of when we think about steric factor, steric hindrance to the approach of the nucleophile, which favors the attack at the less substituted allyl terminus. And third important factor is electronic effects of the substituents of the allyl unit. And fourth important factor is the stability of the initial olefin palladium zero complex. However, in general palladium catalyzed reaction, steric control dominates and attack preferably occurs at the least hindered terminus. Let's talk about the stereochemistry involved in TSUJI-TROST allylation reaction. The stereochemistry of the reaction is depends on the nucleophiles such as soft versus hard nucleophiles. For example, now you take this allylic substrate. So when we use palladium zero catalysis, which quickly undergo oxidative addition along with inversion. So why inversion here? Since top phase is sterically crowded, therefore that palladium zero only interact by bottom phase, which generate this corresponding pi allyl palladium complex. So in this complex, R1 is bulky group when compared to the R2. When we use soft nucleophiles, so which readily attack this carbon. Why this carbon? This carbon is less sterically hindered when compared to the R1, then followed by substitution with inversion that produce this corresponding allylic substitution product. Now closely look the stereochemistry of this nucleophile. So which means that nucleophile attack takes place by top phase, since bottom phase is sterically crowded by this palladium species. So which produce this corresponding product with this stereochemistry. So when we use hard nucleophile, the mechanism is slightly different. So the initial step is just similar to our previous case. So palladium zero catalysis interact with this allylic compound which generate this corresponding pi allyl palladium complex with inversion. So when we use hard nucleophiles which readily undergo transmetalation with this palladium center, so this transmetalation takes place by bottom phase and followed by reductive elimination which generate this allylic substitution product with this respective stereochemistry. Next, moving on. Next, we are going to see the leaving groups involved in TSUJI-TROST allylation reaction. So we have already discussed there are a lot of leaving groups can be useful for this TSUJI-TROST allylation reaction. So here you see some of the examples such as allylic acetate, allylic carbonate, allylic carbamate, allylic phosphate, allylic alcohol, allylic chloride, and etc. And most importantly, we can use vinyl epoxide and vinyl cyclopropane for this TSUJI-TROST allylation reaction. So in case of their order of reactivity of the various leaving groups which follows this trend, so allylic chloride is more reactive when compared to the allylic carbonate, allylic acetate, and allylic alcohol. So allylic alcohol is one of the least reactive in TSUJI-TROST allylation reaction. So when it moving on soft nucleophiles, there are lot of carbon-based soft nucleophiles can be useful for this TSUJI-TROST allylation reaction. So here you can see that various active methylene compounds can be useful and even enamines also useful for this TSUJI-TROST allylation reaction. So in case of hard nucleophiles, organolithium or organomagnesium compounds act as a hard nucleophiles in this TSUJI-TROST allylation reaction. So let's moving on examples based on TSUJI-TROST reaction. So this is the first example. So now you can see that. So here the allylic acetate part is present when we use palladium catalysis, which generate their corresponding pi-allyl palladium species, so which readily react with this soft nucleophile. So this is the active methylene compound. So this carbon, this particular center that attacks the terminal carbon, since terminal carbon is preferred in palladium catalyzed reaction, which produce this corresponding allylic substitution product. Next, moving on, our second example. So here you can see that this part is allylic acetate part. When we use palladium catalysis, we generate their corresponding pi-allyl palladium species in this particular center. And same time, when we use sodium hydride, that readily takes the proton from this center, then produce their corresponding inlet ion. That inlet ion readily attack this terminal carbon to produce this corresponding allylic substitution product. So here DBPE act as a ligand for this reaction. So let's moving on. So here you can see that. So this is the allylic carbonate, and this one is a act as a soft nucleophiles. And when we use palladium catalysis, so which quickly kick off carbon dioxide gas, we generate this corresponding pi-allyl palladium species. Now this ethoxide ion takes the proton from this particular substrate, which generate this corresponding anion. Now this readily attack this carbon to produce this corresponding allylic substitution product. This is our next example. So here you can see that our allylic substrate has two leaving group. One is acetate and another one is a phosphate. However, this phosphate group is more reactive when compared to the allylic acetate part. So therefore, initial allylic substitution takes place this particular carbon under palladium catalysis. So we generate this corresponding allylic substitution product. So here we should note it down the stereochemistry of alkene geometry. So initially this stereochemistry is cis stereochemistry. However, after this reaction which produce trans stereochemistry. So this one is not isolated, since this part also allylic acetate part. So further one more TSUJI-TROST reaction takes place, this particular part that generate this corresponding allylic substitution product. So let's see how this reaction takes place and how the stereochemistry of alkene geometry also changed. So for that, so initially when this allylic substrate react with palladium 0, we generate this corresponding pi complex. Now this pi complex quickly undergo isomerization, which leads to generate this corresponding sigma complex. So once generate the sigma complex, this carbon-carbon bond is rotatable. So resulting that generate this corresponding pi complex. So now this pi complex react with our soft nucleophiles, especially the soft carbon nucleophiles, so which readily attack this terminal carbon, which generate this corresponding allylic substitution product. Now this allylic part undergo one more TSUJI-TROST reaction. So we generate this corresponding pi-allyl palladium species. Now this dimethylamine react with this terminal carbon of pi-allyl complex, so which produce this corresponding allylic substitution product. Let's moving on. So this is our next example. So vinyl epoxide also useful for TSUJI-TROST reaction. So for that, here you can see that vinyl epoxide, when we use palladium 0 catalysis, so initially here you can see that our palladium 0 coordinate with our alkene, then followed by epoxide ring opening takes place to produce this corresponding pi-allyl complex. So now this pi-allyl complex reacts with various nucleophiles which produce their corresponding allylic alcohols, especially substituted allylic alcohols. So here we can see that some of the example. So this substrate react with these soft nucleophiles in the presence of palladium tetrakase and TPP act as a ligand. So initially what happened? the epoxy ring opening takes place. So resulting that generate this corresponding pi allyl palladium complex. Our nucleophile attack takes place by terminal carbon. Why terminal carbon? So this carbon is sterically hindered when compared to this carbon. Therefore, this attack takes place only by this terminal carbon, which produce this corresponding allylic substitution product. So let's moving on. Vinyl cyclopropane. So vinyl cyclopropane also useful for TSUJI-TROST reaction. So here you can see that. So this is the allylic fragment when we use palladium tetrakase, so which readily produce their corresponding pi allyl palladium species and followed by ring open of cyclopropane, which generate this corresponding palladium pi allyl complex. Now here you can see that. So this one acts as a nucleophile. Now this nucleophile attack this carbon, so which produce this corresponding five-membered ring system, five-membered fused ring system. So why not this carbon? Because when we close this ring system here, that could generate three-membered ring system, which one is a strained ring system. Therefore, this one prefer to form the five-membered ring system. So next, moving on, some more example. Now you can see that. So amine nucleophiles also useful for TSUJI-TROST reaction. So when we use palladium catalysis that generate their corresponding palladium complex, now our amine nucleophile which react this particular center, since this one is a terminal carbon, when it forms the pi allyl complex, which generate this corresponding allylic substitution product. So let's moving on some more example. So this example involved with stereochemistry. So why this particular stereochemistry takes place? So let's see. So when we use palladium zero catalysis, here you can see that top phase is sterically crowded with R as well as acetate leaving group. Therefore, our palladium zero should interact with alkene by bottom phase. So resulting that generate this corresponding palladium pi complex. Now this palladium pi complex undergo oxidative addition, which kick off this acetate leaving group, which generate this corresponding pi allyl palladium complex. So now you can see that this palladium species present at the bottom phase. Now nucleophile which readily attack by top phase this pi allyl species, which produce this corresponding allylic substitution product with this respective stereochemistry. So here you can see that one of the example. So this is the allylic carbonate group is present here. So when we use palladium acetate and this mixture tetrabutyl ammonium chloride, and this one act as a ligand and sodium bicarbonate act as a base. So initially what happened? Our pi allyl palladium complex formation takes place. That specifically that pi complex formation takes place by top phase. Since here you can see that these two groups are present at the bottom phase, therefore our palladium should interact with this alkene by top phase. Then followed by this amine group, especially this amide NH2 groups act as a nucleophile in this reaction, which generate this corresponding allylic substitution product. Let's moving on some more example. So this is the another example. This one is the example of intramolecular TSUJI-TROST reaction. Palladium tetrakase is used in this reaction. So when we use palladium tetrakase, palladium zero catalysis, which could generate this corresponding pi allyl palladium species. Now you can see that there are two possibilities. This amine nucleophile then attack this carbon or this carbon. So here you can count that. So if this amine attack this carbon, 1, 2, 3, 4, 5, 6, 7-member ring could be formed. In case of amine, react with this carbon, 1, 2, 3, 4, 5-member ring is formed. So therefore, the formation of 5-member ring is preferred when compared to the 7-member ring. Therefore, so this attack is predominant to produce this fused 5-membered ring system. Next, moving on. So this is our next example. Vinyl epoxide react with these carbon soft nucleophiles in the presence of palladium catalysis. So now imagine that this epoxide ring system present at the top phase. So therefore our palladium species should interact with this alkene by bottom phase. So resulting that generate this corresponding palladium species. Now nucleophile which readily react by top phase since bottom phase is sterically crowded with this palladium species which generate this corresponding product with this respective stereochemistry. This is our next example. So this example you can see that how nucleophile controls the stereoselectivity in TSUJI-TROST reaction. So when we use palladium acetate and triphenyl phosphine, which could generate their corresponding pi-allyl palladium species, which then react with this nucleophile, which generate this corresponding product with their respective stereochemistry. So how the stereochemistry is achieved? So let's see. So when we use palladium acetate and triphenyl phosphine, so that could generate their corresponding pi-allyl palladium species. Now this one act as a nucleophile, so that generate their corresponding unilate ion. Now you can say that the formation of unilate ion that destroys the stereochemistry of this particular carbon, now which could generate this corresponding inlet ion. So now you can see that the top phase is sterically crowded with this isopropyl group. Therefore, our nucleophile should approach by bottom phase. So here you can see that. So this electron moves here. Now this pi electron attack this terminal carbon of pi allyl complex by bottom phase. So resulting that generate this corresponding allyl substitution product. Next, we are moving on asymmetric TSUJI-TROST reaction. So in order to conduct asymmetric TSUJI-TROST reaction, we need suitable chiral ligand. So let's see this example. So here you can see that a racemic allylic acetate which react with this soft carbon nucleophile in the presence of palladium catalysis and this PN chiral ligand. So initially what happened, this palladium catalysis react with this chiral PN ligand which could generate their corresponding palladium complex. Now that palladium complex now interact with our allylic substrate which produce this corresponding pi-allyl palladium species. Now you closely look this particular intermediate. So this intermediate is sterically more hindered with this chiral ligand system. So here you can see that this oxazolene ring system has one isopropyl group. That isopropyl group present at the bottom phase that could blocks the bottom phase completely. So in case of in electronic wise, this particular pi-allyl palladium species, this allylic fragment electronics is affected by this particular ligand system. So here you can see that this phosphorus is electron rich phosphorus. So that could affect the electronic nature of this pi-allyl fragment, particularly in transfusion. So this particular carbon electronics affected by this phosphorus atom in case of this particular carbon electronics affected by this nitrogen atom. Therefore, so the electronic nature of these two carbon is not same at all. So therefore, this carbon is electron rich. In case of this carbon is electron deficient. So therefore, there are cooperative stereo and electronics involved in this chiral ligand system, which makes that. So here you can see that now soft nucleophile readily attack this particular carbon since this carbon is electron deficient when compared to this carbon. So this particular attack where it takes place. So this particular attack takes place by top phase since bottom phase is sterically crowded. So resulting that generate this corresponding allylic substitution product with high enantiomer selectivity. So particularly this asymmetric TSUJI-TROST reaction is highly useful for synthesis of various pharmaceutical ingredients and natural product synthesis. So let's moving on our next example. So TSUJI-TROST reaction involving with cycloaddition reaction. So for that now you take this particular substrate. So here you can see that allylic acetate fragments are there in this substrate. When it interact with palladium 0 catalysis, we know that can generate their corresponding pi allyl palladium species. So now you can see that this acetate act as a leaving group. So once interact with palladium 0 that kick off as a acetate ion. Now this acetate ion readily attack the silyl group which kick off silyl group which generate this corresponding intermediate. So this intermediate is equal to this dipole fragment. So here you can see that. So this one act as a nucleophile in case of this allyl fragment act as a electron deficient fragment. So therefore this can readily react with some of activator alkene that can undergo cycloaddition reaction. So for that now you take this example. So this one is a alpha beta unsaturated alkene. So here this alkene react with this allylic substrate in the presence of palladium acetate and suitable phosphine ligand that generate this corresponding fused product. Let's look by magnetically. So this pi allyl palladium complex formation we already seen in our previous scheme. So now this negative charge that attack this particular alkene carbon, therefore this pi electron now shift here, then followed by this pi electron move towards the oxygen atom. So resulting that generate this corresponding intermediate. Now this negative charge moves here, then this pi electron attack this particular carbon. So resulting that generate this corresponding species, then followed by decomplexation which produce this corresponding product. Up to now, we have seen various soft nucleophiles involved in TSUJI-TROST reaction. So next we are going to see how hard nucleophiles involved in TSUJI-TROST reaction. So hard nucleophiles, for example, here you can see that. So this is the allylic lactone which react with this organo-zinc reagent in the presence of palladium tetrakase. So which produce this corresponding allylic substitution product. Let's think about how this reaction worked to produce this corresponding product with this respective stereochemistry. So initially, you just imagine that, so this lactone ring system present at the top phase, therefore our palladium should interact with this alkene by bottom phase, therefore palladium now coordinate with this alkene by bottom phase and followed by oxidative addition takes place by bottom phase which could generate their corresponding pi allyl palladium species. Now this organo-zinc reagent undergo by transmetalation with palladium center. Since already palladium present at the bottom phase, the transmetalation should take place by bottom phase and followed by reductive elimination also takes place by bottom phase to produce this corresponding product with this respective stereochemistry. So here hard carbon nucleophiles means that pKa more than 25, we can say that hard carbon nucleophiles including organometallic compounds such as organo-zinc, organoborane, organoaluminium, organo-tin and organosilane compounds. So those all the substrates undergo by transmetallation pathway. Let's see one more example. So here you can see that. So here there are two acetate leaving group present at this carbon, so which react with organostenane in the presence of palladium tetrakase that generate this corresponding product. So here what happened? Two allylic substitution reaction takes place to produce this respective product. So let's see magnetically how this reaction takes place. So initially, when it interact with palladium complex that generate this corresponding pi allyl palladium species, now this organo-tin species that undergo transmetallation with this palladium center which generate this corresponding intermediate, now followed by reductive elimination to produce this corresponding product. Now again, so this one is a allylic fragment with leaving group. So therefore one more TSUJI-TROST allylation reaction here going to take place to produce this corresponding pi allyl palladium species. Now once again this transmetalation reaction takes place where this organostenane which produce this corresponding intermediate then followed by reductive elimination to produce this corresponding product. Okay, let's moving on our TSUJI-TROST reaction summary. So we have seen that what is mean TSUJI-TROST reaction and their catalytic cycle and how the mechanism is differs when we use hard and soft nucleophiles, and followed by we have seen that how stereochemistry also change when we use hard nucleophiles and soft nucleophiles, and followed by we have seen that various examples involved in soft nucleophiles as well as hard carbon nucleophiles. So especially we seen that asymmetric TSUJI-TROST reaction, as well as we seen that how vinyl cyclopropane and vinyl epoxide involved in TSUJI-TROST reaction. The TSUJI-TROST reaction has broad application in synthesis of various natural products, pharmaceutical intermediates, agrochemicals, and complex molecules with chiral centers. And that's it for TSUJI-TROST reaction. So if you enjoyed this session, just to give it a thumbs up and share it with your friends, and don't forget to subscribe ChemOrgChem for much more content like this. So here you can see that there are various practice problems. So when you get a free time, you just give it a try. So the answers will be discussed in our next videos. And finally, thanks for watching. Bye bye.